Hi again and welcome back. In the previous video lecture we gave a few definitions, some absolutely new concepts such as that of a bounded signal and a stable dynamical signal system in the BIBO sense, in the bounded input, bounded output sense. So let's go through these things once again very quickly. We said that the signal is said to be bounded if there is a number m, so that the absolute value of the signal never exceeds m. Or graphically, if we can sketch the graph of x within a horizontal band of radius m. Then a dynamical system, we said that we will call it stable in the BIBO sense, BIBO stable in the bounded input, bounded output sense, if the output of the system is bounded, whenever the input is bounded. And we wrote it concisely like that. Then we can also define the notion of an unstable dynamical system. So if it is not BIBO stable, we will simply call it BIBO unstable. Just let me say what this means. It means that there is a bounded input that can produce a not bounded or unbounded output. Okay, so far so good. So these are new definitions. And then we recalled what is the impulse response of a dynamical system. If we know the transfer function, if we know that the transfer function is g uppercase, then the impulse response is simply the inverse Laplace transform of the transfer function. So L-1 of g uppercase. And then we used the impulse response in this theorem to tell whether a system is BIBO stable. Because if you remember, it turned out it's quite difficult to use the definition directly to tell whether a system is stable. So the theorem here says that a dynamical system with an impulse response g lowercase is BIBO stable if and only if this g lowercase is absolutely integrable. And what does this mean? It means that the integral from 0 to infinity of the absolute value of g with respect to time is a finite number. We proved half of this theorem. We actually proved that if g is absolutely integrable, then the system is BIBO stable. And to do that, we used this very significantly, very important property that the output of the system x of t is the convolution of the input with the impulse response of the system. So this is what we did last time. Now we can use this theorem. I will leave this there. So we can now use this theorem and we can apply it to a few examples where g is a rational function. So g is p over q, p and q are polynomials, and we take them to be coprime. Coprime means that they share no roots. We cannot factorize p and q and then eliminate any terms or factors inside there. So this is a rational transfer function. Recall that if the degree of p is no larger than the degree of q, then we say that this rational function is proper. And if this happens, we say that it is strictly proper. Now let's have a look at the first very simple example where we have a rational function of this very simple form. G of s is 1 over s minus a, where we have a simple pole here. So the only pole we have is a. We will be using this theorem. Okay, so to use it, we need to know the impulse response g lowercase. So in that case, g lowercase of t is e to the at, the inverse Laplace transform of that, defined for t non-negative. Is that transfer function integrable, absolutely integrable, or not? That's the question, because if and only if it is, then the system is BIBO stable. We can see here that if this a is positive, then the impulse response goes to infinity. So the area under the curve, of course, again, goes to infinity. So if a is positive, then the system is unstable. If a is 0, then this is equal to 1. It is constant, equal to 1. Again, the area under the curve you see very clearly that goes to infinity. So even in that case, the system is unstable. Just to be very clear, what we're doing here is that we're asking whether this integral from 0 to infinity, we're asking whether that holds. But for this to hold, it is absolutely necessary that g goes to 0. If it doesn't, this is for sure not convergent. Now the third case is e to the at, where a is negative. And we can tell here, actually we did that in the previous video, but you can try it yourselves as an exercise. You can tell here that this is indeed absolutely integrable, meaning that this area here is indeed finite. And this means, according to that theorem, that the system now is BIBO stable. So when it comes to this system, where we have just one pole, one real pole positioned at A, that the system is stable if and only if A is negative. So let's sketch it over here. Let's make a little nice sketch. If the pole A is negative, then the system is stable. If the pole is at 0, then the system is unstable. If the pole is here, then again the system is unstable. Let's have a look at another example. What if the poles are double? Well, we have some similar situation. So what happens in these cases now? So this is a double pole. So again, the question here is this stable or unstable? For what values of A might this be stable? A is a real number. A is a pole of the system with multiplicity 2. And now we can see here that the impulse response is t times exponential of at. And following the same line of thought as before, we can see that this is BIBO stable if and only if A is negative. I will leave this to you to verify as an exercise, but the important term here, the important and dominant part, is this term, the exponential. This determines whether the function decreases and vanishes adequately fast so that it is absolutely integrable, or it goes to infinity, so it is not, or it remains equal, this remains equal to 1, so this becomes equal to t if A is 0. So again, this is not absolutely integrable, meaning that the system is of course not BIBO stable. So even in this case, we can derive exactly the same conclusions, that in these two cases, the system is unstable. In this case, the system is stable. We haven't proven anything yet, but it seems that the stable region is on the left of the imaginary axis. We haven't examined so many other cases, like for example, what happens if we have different numerators here or different denominators. We're focusing only on simple cases, but nevertheless, it seems that we might be looking at a situation where if we're on the left of the imaginary axis, we have a stable system. And if we're on the right, we have an unstable system. Let's examine one more case. Let's see what happens on the imaginary axis. So let's say we have the poles JB and minus JB. We have purely imaginary poles. This is an example of a function that has only imaginary poles. We'll follow exactly the same procedure. We'll determine the inverse Laplace transform g of t is, take b not b equal to 0. Then we can see that this is a sinusoidal function. This is g, and this is g absolute value. And the area grows and goes to infinity. The area under the curve goes to infinity, which means that this is not absolutely integrable, which means that the system is BIBO unstable. So in this case, the system is BIBO unstable if we have these poles. So once again, if we're so far when we are purely on the left, strictly on the left of the imaginary axis, it seems we're stable. If we are here, we are unstable. If we're on the axis, we are unstable. And again, here, if we are on the axis, it seems we are unstable. But let's give one more example to see what happens. Let us now examine this case. What happens if we have a pair of complex conjugate poles? And that will be g of s is 1 over s minus a squared plus b squared. Just to be clear, what are the poles of this transfer function? The poles are the roots of the characteristic polynomial, which is this, the denominator here, which are a plus j b. And what is the inverse Laplace transform? What is g lowercase of t? This is 1 over b times a sine times an exponential. So exponential of at times sine of bt. We discussed about these things when we introduced the inverse Laplace transform, and you see here that the real part a determines the rate of growth or rate of decay, and the imaginary part b determines the frequency. So this is a beautiful result. But it turns out that, okay, this is always bounded. This either goes to infinity or remains constant if a is 0, or decays exponentially fast and goes to 0. And indeed, as in the previous cases, if a is negative, then we're looking at something like that, which decays exponentially fast, and the integral of this function, of the absolute value of g, I'm not going to compute this integral, but you can do it yourselves as an exercise. So this integral now is finite, only in this case. Why? Because if a is 0, then we have a sinusoidal wave. And we showed before that this is not absolutely integrable. And if a is positive, this is for a is 0. And if a is positive, then this grows exponentially. So again, this is not absolutely integrable. What do we conclude in this case? We conclude that a determines whether this is BIBO stable or not. So in this case, if we're on the left, if the real part is negative, this is a stable case. So this is stable. If we are on the right, if we have a pair of poles with a positive real part, then this will be an unstable example. One more case, last one, just a last example. But you see, we do the same thing over and over again. It's also a good opportunity to practice this theorem. Let's have a look now at one last example. We have examined all these cases. What happens if we are on the real line, on the left and on the right? What happens if we have double real poles on the left and on the right of the imaginary axis? What happens if we have purely imaginary poles? What happens if we have a pair of complex conjugate poles either on the left of the imaginary axis or on the right? One last example that may be interesting to have a look at is what happens if we again have a pair of complex conjugate poles, but they have a multiplicity of 2, they are double poles. So what happens in this case and what happens in that case? Again, let's not get ahead of ourselves, but we can suspect that this will be the stable case and this will be the unstable one. But let's see why. We will again apply this theorem. What is a transfer function that has a double pair? It is this one over here. So the multiplicity 2 comes from this square over here. And what is g of t? So it is a scalar, a constant, times an exponential, like before, times sine. So here we have an oscillatory behavior, of course, due to the imaginary component in the poles, minus this function over here. Now we can tell that this part, the first function, sine, is bounded. The second function grows, okay, because we have a multiplication by t, so it grows either to plus infinity or minus infinity, but it grows rather slowly, or to put it better, it grows much slower than this function. So the dominant function, again, the dominant part, is the exponential. This can grow like that. The exponential grows much, much faster. So this determines whether this is absolutely integrable or not. And it will be only if a is negative. Let us not compute integrals and so on here, but trust me, if a is negative, then this goes to 0 very fast, and this whole function is absolutely integrable. Otherwise, if a is positive or 0, then this will be not integrable and will not have a BIBO stable system. So this is BIBO stable, this is BIBO unstable. Let's have a look at these slides over here that summarize our results. So when we have poles that are on the left-hand side of the imaginary axis and they are real poles, we said that we have a BIBO stable system. Wherever these poles might be, actually. We haven't shown that, but this is the result that we will present in this video lecture. So when the poles are on the left-hand side of the imaginary axis, when the real part of the poles is negative, then we have BIBO stability. If we have even one pole on the right-hand side, then the system is BIBO unstable. If we have even one pole at 0, then the system is again BIBO unstable. If we have a pair of purely imaginary poles, we're unstable. If we have poles, even a single one with a positive real part, we are unstable. It has become somehow clear, at least intuitively, that there is a relationship between the poles of the transfer function and whether the system is stable. This is very nice now because we are able to tell whether a system is stable based on the transfer function, not the impulse response. At least when the transfer function is a rational function and it is also proper. It is given by a quotient of polynomials. We have the following result, which we haven't proven here, but you can find the proof in the textbook. So this theorem states that G is BIBO stable if and only if all of its poles have a negative real part. This allows us now to talk about a stable region in the complex plane. If the poles are positioned in the open left-hand side of the complex plane on the left of the imaginary axis, so inside here, as many poles as you like, you can have here as many poles as you like, then the system is BIBO stable. The poles can also be of any multiplicity. If you have even one pole on the right-hand side, for example here, then the system will be unstable. If you have even one pole on the imaginary axis, then the system will be again unstable. This theorem, as opposed to the previous version, the one that we introduced in the previous lectures, in the previous video lecture, has the advantage that we don't need the impulse response to tell whether the system is stable. We can link stability with properties of the transfer function itself. So this is one advantage. And the second one is that we don't need the impulse response, which is not always available. We can now use this to show just a few examples. I will leave this here for reference. Take this transfer function. What are the poles? Just one pole over here, -10. It has a negative real part, so the system is stable. Take another one. So this has 3 poles, all of them are real. What are the poles here? They are -1, -2, -3. All of them are negative. All of them have a negative real part. Therefore, this system is BIBO stable as well. Let's have a look at this following example. This is a proper transfer function. The degree of the numerator does not exceed that of the denominator. So we can apply the theorem. Let's check the poles. We don't care about the numerator. It is not relevant for the stability of the transfer function. We will just focus on the denominator, this one. What poles do we have here? We have -1 plus minus j. -1 plus minus j. What is the real part here? It is -1, which is negative. Therefore, this is also BIBO stable. Let's have a look at an unstable example now. We saw before, over here, that this system has the poles -1, -2, -3, therefore it is stable. Let me say that again. If you have here s plus 5 or even s minus 5, whatever you have here, absolutely doesn't matter as far as the stability of the system is concerned. If we introduce here one more term, s squared plus 1, then the poles will be -1, -2, -3, plus minus j. So the poles are here, 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 -1, -2, -3, and here, plus j and minus j. These are stable poles, but these two, this pair of imaginary poles, makes the whole system unstable. So the system is unstable just because of this term. This spoils everything. One last example, we'll leave it as an open question because we cannot answer it so far, is the following. Polynomial over polynomial. What are the poles of this transfer function? We don't know, and it is not too easy to tell. As far as I can tell, I selected the coefficients arbitrarily, but it doesn't seem we can apply Horner's method to find rational roots of this polynomial. So it turns out it's difficult to determine the poles of G. So we cannot apply the theorem we stated before, unfortunately, unless we have the denominator of G available in a nice factorized form, so it becomes clear what the poles are. We are not able to apply that theorem. I will leave this now here as an open question. We are able to answer it, but not yet. So here's an open question for us to address in the next video lecture. And until next time, bye.